Go ahead and put your hand flat on the table right now. Do it. Feel that? Feels pretty real, doesn't it? Feels solid. Now let me tell you something that should genuinely disturb you. That table, your hand, everything in this room is constructed almost entirely out of emptiness. Not metaphorically, not poetically. This is a verified laboratory-confirmed fact. The atoms making up every object you've ever touched are more than 99.99% empty space. And here's a number to really sit with. If you gathered every human being on Earth, all 7 billion of us, and stripped out all that empty space from every atom in every body, you could fit the whole of humanity into a volume roughly the size of a sugar cube. Something you could pinch between 2 fingers. 7 billion people. 1 sugar cube. And yet, you cannot walk through walls. Isn't that strange? Shouldn't you be able to? If everything is mostly nothing, why does anything feel solid at all? That question is what we're going to dig into today, and I promise you the answer is far weirder, far more beautiful, and far more satisfying than you might expect. Here's what we're going to do. We're going to trace this puzzle right down to its roots. We're going to figure out what atoms actually are, not the cartoon version, the real version. We're going to discover what makes atoms occupy space at all. And we're going to find that the reason you bounce off a wall when you walk into one has almost nothing to do with atoms crashing into each other like little billiard balls. The real explanation lives deep inside quantum mechanics, in a principle so fundamental that without it, not just walls, but you yourself would not exist. So let's start from the beginning. You push on a wall, it pushes back. Newton, right? Action and reaction. But what's really happening down there at the atomic level? At the surface of your hand you have atoms, carbon, hydrogen, oxygen, nitrogen. At the surface of the wall there are more atoms, silicon, calcium, oxygen. When you push, you're bringing your atoms close to theirs. But how close can they actually get? What happens as they approach each other? This is where things start getting interesting. Back in the early part of the last century, a fellow named Ernest Rutherford working in Manchester decided he wanted to peer inside the atom. The fashionable idea at the time was J.J. Thomson's plum pudding model. Thomson imagined the atom as a kind of diffuse blob of positive charge with electrons dotted through it, the way raisins sit in a cake. Very domestic, very British. The positive charge was thought to be spread uniformly throughout the whole atom, with electrons just lounging around embedded in this positive goo. Rutherford wasn't so sure. He wanted to test it, so he set his students Geiger and Marsden to work firing alpha particles, which are essentially helium nuclei, 2 protons and 2 neutrons bonded together, positively charged and moving fast, at an extremely thin sheet of gold foil. The idea was simple enough. Shoot these tiny projectiles at the gold atoms and see how they scatter. If the plum pudding model was right, you'd expect the alpha particles to sail straight through with maybe a gentle deflection here and there. The positive charge is all spread out, so the electrical force on any passing alpha particle would never get very strong, like a bullet through cotton candy. A little wobble, nothing dramatic. And sure enough, most of the alpha particles went right through, no surprise. But then something happened that nobody was prepared for. Some of the alpha particles bounced backwards, not nudged sideways, bounced back toward where they came from. Rutherford himself described it, and I love this. He said it was as if you fired a large artillery shell at a sheet of tissue paper and the shell came back and hit you. Think about that image for a moment. A cannonball bouncing off tissue paper. That doesn't happen unless there's something extremely hard, extremely concentrated hiding inside that tissue. Rutherford understood immediately what it meant. The positive charge isn't smeared out. It's all packed into a tiny, dense core at the center of the atom, a nucleus. And everything else in the atom is empty space. How tiny is the nucleus compared to the atom? About 100,000 times smaller. Let me paint you a picture. If you scaled an atom up to the size of a football stadium, the nucleus sitting at the center would be roughly the size of a marble on the 50-yard line. The rest of the stadium, the seats, the air, all of it, is empty, vacant, nothing. So now you've got a real puzzle. If atoms are virtually all empty space with a tiny nucleus in the middle and some even tinier electrons somewhere out in that vast emptiness, why can't things pass through each other? Why don't the open spaces in your atoms line up with the open spaces in the wall's atoms and let you glide right through? The stadium has plenty of room. Why can't the marble from one stadium drift through the empty space of another? To answer that, we need to understand what electrons are really doing out there. The old mental picture has electrons circling the nucleus like planets around the sun. Neat little orbits, precise trajectories, everything tidy. That picture is wrong, completely wrong. Electrons don't follow orbits. They don't have definite positions. They don't have definite paths. An electron is not a little ball sitting somewhere specific. It exists as what we call a probability cloud, a spread out, smeared out region that tells you the probability of finding the electron at any given location if you were to measure it. Between measurements, the electron isn't really anywhere in particular. In some sense, it's everywhere in that cloud simultaneously. Now you might ask, why doesn't the electron just fall into the nucleus? The electron carries negative charge, the nucleus carries positive charge. Opposite charges attract, so what stops them from crashing together? This is where Werner Heisenberg enters the story with his uncertainty principle. Heisenberg worked out that there is a hard limit in nature on how precisely you can simultaneously know a particle's position and its momentum. Pin down its location tightly, and its momentum becomes wildly uncertain. Pin down its momentum precisely, and you lose track of where it is. It's not a limitation of our instruments. It's a feature of reality itself. Now watch what happens when you try to squeeze an electron into a very small region, say, down to the size of a nucleus. You'd be constraining its position very tightly. The uncertainty principle immediately demands that its momentum become very uncertain, which means the electron could be moving extremely fast. And fast movement means large kinetic energy. So the tighter you confine the electron, the more energy it's forced to carry. Compression costs energy. The electron finds a natural resting distance from the nucleus, where the electrical attraction pulling it inward is balanced against this quantum mechanical energy cost of being confined. That balance defines the size of the atom. Not too close, not too far, just where the uncertainty principle and the electrical force reach an equilibrium. The electron cloud that results from this balance is what physically occupies the space of the atom. So when you push on a wall, what's actually colliding are these electron clouds, the fuzzy quantum smear of your atoms meeting the fuzzy quantum smear of the wall's atoms. Now electrons all carry negative charge, and like charges repel, so yes, when electron clouds start to overlap, there is electrical repulsion. That's real, and it matters. It's the same basic force that makes two magnets with matching poles resist being pushed together. When your hand presses against the wall, the electron clouds are being pushed into proximity, and they push back electrically. But is that the whole story? Just electrical repulsion? It turns out no. There's something else happening, something deeper, and this is the part that really blew my mind when I first understood it. In 1925, an Austrian physicist named Wolfgang Pauli made a discovery that changed everything. Pauli was brilliant, famously sharp, not particularly patient with sloppy thinking. He found that electrons carry a property called spin. Now, spin in quantum mechanics is not what you're picturing. It's not the electron physically rotating like a tiny top. It's an intrinsic quantum property, and it comes in exactly two varieties, which we call spin up and spin down. That's it. Two options. Here's where it gets profound. Pauli found that no two electrons in the same system can ever be in precisely the same quantum state. If two electrons are in the same location with the same energy and everything else identical, one has to be spin up and one has to be spin down. Fill those two slots, and you're done. A third electron cannot join them. There is no room in the quantum sense. This is the Pauli Exclusion Principle. Electrons belong to a class of particles called fermions. And fermions are deeply, constitutionally antisocial. They refuse to share a quantum state with another fermion. Now think about what this means when you push your hand toward the wall. As the electron clouds begin to overlap, if electrons could simply pile into the same quantum state without restriction, the clouds would merge together, matter would compress. Things could pass through things, but electrons cannot do this. The exclusion principle forbids it absolutely. As the clouds try to occupy the same region of space, the electrons are forced to climb into different higher energy quantum states. And that process costs energy, a lot of energy. The more you compress, the more it costs. Imagine trying to stuff more marbles into a jar that is already packed completely full. You can't just squeeze them in. Something has to give. That resistance you'd feel pushing against a jar of packed marbles, that's the rough intuition for what electron clouds are doing when atoms get too close. The electrons have nowhere else to go quantum mechanically, and so they push back. This resistance is sometimes called degeneracy pressure, though the physics is what matters more than the name. The bottom line is that it's the Pauli Exclusion Principle, not just electrical repulsion, that is primarily responsible for the solidity of matter. Feynman himself put it memorably. He said something to the effect that it is precisely because electrons cannot all pile on top of each other that tables and everything else are solid. If you could stack all electrons into the same state, matter would collapse in on itself to an incomprehensible degree. The exclusion principle prevents that. So there are really two things working together when your hand meets the wall. First, the electron clouds repel each other electrically. Second, and more fundamentally, the exclusion principle prevents electrons from sharing quantum states, creating an energy cost that grows enormous as you try to push atoms together. Both effects combine to make matter impenetrable. Let me give you a way to picture this. Imagine you're at a very crowded party and everyone is trying to squeeze into the same corner. But there's a strict house rule. No two guests can occupy exactly the same spot. So people spread out. They take up space. If you try to push more guests into that corner, they push back, not because they're physically colliding particularly, but because the rule of the party says they cannot overlap. Electrons are doing exactly that. They spread out to fill available quantum states. When you try to force more of them into the same space, they resist. That's why you can't walk through walls. Now, I suspect some of you are thinking about quantum tunneling. You've heard about it. Particles passing through barriers they classically shouldn't be able to cross. Does that mean you could, at least in principle, quantum tunnel through a wall? Let's be honest about this, because yes, tunneling is real, and no, you will not be tunneling through any walls. Here's how tunneling works. In classical physics, if a ball lacks the energy to roll over a hill, it rolls back. Full stop, no exceptions. In quantum mechanics, particles have wave-like properties, and when a wave hits a barrier, it doesn't simply stop at the boundary, it penetrates into the barrier, decaying exponentially as it goes. If the barrier is thin enough, a small remnant of the wave emerges on the other side. That remnant represents a genuine probability that the particle will be found beyond the barrier. It didn't go over, it didn't go around, it appeared on the other side, as if it teleported. This is not a theoretical curiosity. The scanning tunneling microscope works because electrons tunnel between a sharp metal tip and a surface, letting us image individual atoms. Nuclear fusion inside stars happens partly because protons tunnel through the electrical barrier that would otherwise keep them apart. Radioactive alpha decay happens because alpha particles tunnel out of nuclei. Tunneling is absolutely real. But the probability of tunneling depends critically on three things: the mass of the particle, the thickness of the barrier, and the height of the barrier. Heavier particle, lower probability. Thicker barrier, lower probability. Higher barrier, lower probability. An electron has a mass of about 9 times 10 to the minus 31 kilograms, nearly nothing, and even for an electron tunneling through more than a few atomic widths, just a few tenths of a nanometer, the probability already becomes vanishingly small. A wall is not a few atomic widths thick. A wall is centimeters thick, tens of billions of atomic layers. And you are not a single electron. You're assembled from roughly 7 times 10 to the 27 atoms. That's 7 billion atoms. For you to tunnel through a wall, every single particle in your body would have to tunnel simultaneously in the same direction and then reassemble coherently on the other side. The probability of that happening is something like 10 to the power of negative 10 to the 30th. That number is so far beyond small that no word in ordinary language touches it. If you waited 1 trillion times the age of the universe, you still would not expect this to happen, not even once. So yes, quantum mechanics technically assigns a non-zero probability to you tunneling through a wall, but practically speaking, it is never going to happen. To put it in perspective, your odds of winning the lottery are absolutely gigantic compared to your odds of quantum tunneling through a wall. Winning the lottery every single day for the rest of your life would be mundane compared to tunneling through a wall once. So let's not dwell on that possibility. Let me step back and state the core idea as simply as I can. Everything is made of atoms. Atoms are almost entirely empty space, but the electrons in those atoms obey the Pauli Exclusion Principle, which means no two electrons can occupy the same quantum state. When atoms are pushed together, the electrons resist, because accepting more compression would require sharing quantum states they are forbidden from sharing. That resistance is what you experience as solidity. That's the whole secret. The hardness of tables, the impenetrability of walls, it all comes from that one quantum rule. Now let me clear up a misconception that floats around in popular science. People sometimes think atoms are solid because they're tiny, hard spheres like marbles. When atom marbles meet, marble logic says they can't overlap. Simple. But that picture is completely mistaken. Atoms are not solid spheres. They're probability clouds. The nucleus is tiny. The electrons are spread out in a quantum haze. In a purely classical picture with electrons as little planet-like balls orbiting the nucleus, there's actually no obvious reason why two atoms couldn't interpenetrate. Why couldn't one set of electrons orbit around both nuclei simultaneously? Classically, that's strange, but not forbidden. It's only quantum mechanics, specifically the exclusion principle, that provides the actual reason why matter won't compress without limit. There's also a popular claim you might have heard that we never actually touch anything. That what feels like contact between your hand and a table is really just electrical repulsion between electron clouds, with a tiny gap always remaining. This is a half-truth that tends to mislead more than it illuminates. The nuclei of your atoms and the table's atoms never meet. That part is true. The electron clouds, however, are overlapping and interacting. If that's not touching, what is? The difficulty is that the word touch is a large-scale human world concept. At the atomic level, the concept doesn't translate cleanly. Electrons are genuinely fuzzy, genuinely smeared out. There isn't a sharp boundary to make contact with. What matters physically is that the atoms interact strongly, that they push back, and that this is what your nervous system registers as the feeling of a solid surface. Now let me take you on a thought experiment. Suppose you could shrink yourself to atomic scale and stand on one of your hand's atoms, looking across at an atom in the wall. What would you see? Nothing very clearly, since electrons don't reflect light in any ordinary way. But let's say you have a magical atomic flashlight. You'd see your nucleus, tiny and intense like a distant sun. Around it, far away in relative terms, a misty sphere of electron cloud, and across a vast empty space, the wall atom, its own tiny nucleus, its own misty cloud. As your atom draws closer to the wall atom, you'd feel the resistance building. The clouds are overlapping, and something is pushing back hard. You might think, why not navigate through the gaps in the cloud? The cloud is mostly empty space after all. But here's the thing. The cloud is not a collection of tiny dots with navigable spaces between them. The cloud is the electron. The electron is the cloud. That whole region is quantum mechanically occupied. And because of the exclusion principle, the electrons in your atom cannot move into states already filled by the wall atom's electrons. The resistance you feel is not a physical wall within the atom. It's a quantum mechanical barrier of state occupancy. That's what stops you. Let me ask you something else. What if the exclusion principle simply didn't exist? What if electrons belong to the other family of particles, bosons, rather than fermions? Bosons, particles like photons, don't obey any exclusion principle. They're perfectly happy to pile into the same quantum state. In fact, they prefer it. Given the chance, bosons crowd together enthusiastically. If electrons were bosons, every electron in every atom would immediately collapse into the lowest available energy state right next to the nucleus. Electron clouds would not spread out. Atoms would be much, much smaller. When atoms approached each other, their electrons would have no objection whatsoever to sharing states. They'd merge happily. Matter would not be rigid. It probably wouldn't be meaningfully solid at all. Everything would collapse into dense, undifferentiated blobs. Chemistry would vanish, because chemistry depends entirely on the way electrons arrange themselves into shells and orbitals, and that arrangement only exists because the exclusion principle forces electrons to spread across different states rather than all crowding into one. You wouldn't exist, neither would I. The Pauli Exclusion Principle is not some minor technical detail of atomic physics. It is one of the foundational rules that makes a habitable universe possible. And this isn't just a philosophical observation. In 1967, Freeman Dyson and Andrew Leonard actually proved mathematically that ordinary matter is stable precisely because of the Pauli Exclusion Principle. Without it, the electrical attraction between electrons and nuclei would cause all matter to catastrophically collapse. The exclusion principle provides a kind of pressure, a quantum mechanical resistance to compression that holds matter up. Later, in 1975, Elliott Leib and Walter Thuring found an even cleaner proof, demonstrating rigorously that there is a lower bound on the total energy of any collection of electrons, and that this lower bound depends fundamentally on the exclusion principle. This is the quantum mechanical reason why you cannot squeeze matter down to a point. When you sit in a chair and the chair holds you up, you are literally being supported by the Pauli Exclusion Principle. When a building stands, same thing. When the Earth holds together as a solid body, same thing. There are places in the universe where this principle is tested to its absolute limits. White dwarf stars. A white dwarf is what remains after a star like our sun burns through its fuel. The outer layers drift away and the core is left behind, incredibly dense. The mass of an entire sun compressed to roughly the size of Earth. A teaspoon of this material would weigh many tons. What keeps it from collapsing further under its own enormous gravity? Not fusion. That's finished. Not thermal pressure. The star is cooling. What holds it up is electron degeneracy pressure. The electrons are packed so tightly together that every available quantum state is filled. They are as compressed as the exclusion principle will allow, and they refuse to be compressed further. The same principle keeping your hand off the table is holding a dead star against its own gravitational collapse. If the star is massive enough, gravity eventually overwhelms even this. The electrons get forced so hard into the nuclei that they combine with protons to form neutrons, and you get a neutron star. Neutrons are also fermions. They also obey the exclusion principle. A neutron star is held up by neutrons refusing to share quantum states, and if even that is not enough, if gravity wins completely, you get a black hole. The exclusion principle loses. Everything collapses without limit, a singularity. But for ordinary matter at ordinary scales, the exclusion principle is more than sufficient. It makes atoms take up space. It makes matter solid. It makes walls walls. So come back with me to where we started. Your hand on the table. You feel resistance. Why? Because the electron clouds in your hand's atoms and the electron clouds in the table's atoms are governed by the Pauli exclusion principle. As they approach each other, as they try to overlap, the electrons cannot move into states already occupied. They push back. The hardness of the table, the impenetrability of the wall, that is quantum mechanics operating at the scale of your fingertips. It's one of the great surprises of physics that something so abstract, so mathematical, so deeply strange, manifests as something so utterly ordinary and familiar as the resistance you feel when you lean against a wall. There is no classical force exactly doing this pushing in the way gravity or magnetism push. This is a statistical constraint, a rule about allowable quantum states, and yet it is powerful enough to hold buildings upright, to keep planets solid, to prevent you from sinking through your chair right now as you read this. I find that genuinely astonishing. A young Austrian physicist puzzling over electron configurations in atoms discovers a rule, and that rule turns out to be what holds the physical world together. When you lean against a wall, you're not leaning against bricks. You're leaning against a quantum mechanical principle. The wall is solid because electrons are fermions, and fermions do not share. So if someone asks you why you can't walk through walls, now you know. It's not that atoms are solid balls. It's not just that electrons repel electrically. It's the Pauli exclusion principle. It's quantum mechanics. And the solidity of everything you've ever touched, every surface you've ever pressed against, all of it flows from one simple rule. No two fermions in the same quantum state. That's the whole secret. Now let me leave you with one larger thought. We live in a universe where the quantum rules seem completely alien. Particles are waves. Waves are particles. Position and momentum can't both be known. Electrons don't sit anywhere in particular until you look. It all sounds like something from a dream. And yet out of these bizarre rules comes the ordinary world. The chair you're sitting on, the floor holding you up, the walls standing around you, all of it. The solidity, the structure, the rich chemistry of living things, all of it emerges from quantum mechanics. Fuzzy probability clouds produce hard tables. Uncertainty at the smallest scales produces reliability at the large ones. The exclusion principle takes the inherent randomness of electrons and imposes structure on it. It builds the shells that make the periodic table work. It makes chemistry possible. It makes matter solid. So the next time you walk into a wall, which I genuinely hope is not a frequent occurrence for you, take a small moment to appreciate what's happening. That wall is solid because of one of the most elegant and strange rules in all of nature, and the universe isn't stopping you out of spite. It's simply built a certain way, with certain rules, and those rules have consequences. Remarkable, beautiful, strange, wonderful consequences. Thank you for thinking about this with me. Now here's what I want you to do. Look around you. Pick any ordinary thing you interact with every day, and ask yourself, what strange physics might actually be going on underneath that perfectly ordinary surface? What's your answer?